Hello, I am Dr. Ramesh Ramapanikar. I am an associate professor in chemistry at the Department of Chemistry at Indian Institute of Technology, Kanpur. So today I will be discussing the portions that are covered in Unit 10 of the chemistry book by NCERT for class 12 students. And this particular chapter, as you would know, covers haloalkanes and haloarenes. These class of compounds are also known as alkyl halides and aryl halides. They are a class of organic compounds where a hydrogen atom that is present in a hydrocarbon is replaced by a halogen atom. Multiple hydrogen atoms can also be replaced by multiple number of halogen atoms, and in those cases too they fall under the same category. However, their ideal names are haloalkanes and haloarenes, but you would find that the normally available and most common compounds are generally referred to as alkyl halides rather than haloalkanes. However, a systematic naming would require that we call them as haloalkanes. We should start with the name of the halogen that is attached to the organic compound. So we will deal with the naming of these compounds and how these molecules are classified. Then we would go on to say how they can be prepared from simple starting materials, and finally we would talk about their properties and then look at a few examples of these class of compounds that are useful to mankind, either synthetic or which are available naturally. Now, to begin with, I would like to say that a general representation of these molecules, that is, whenever you would like to show an alkyl halide, that is a haloalkane, by a simple representation, the term that we normally use is Rx, where R stands for the alkyl group, as you already know, and X stands for the halogen atom that is attached to the alkyl group. And in organic molecules, the most common halogen atoms that you would find are fluorine, chlorine, bromine and iodine, and we will not see the fifth halogen atom, the fifth atom that is present in the group 17 element, astatine, that is not normally found in organic molecules. So by haloalkanes we would only mean compounds of fluorine, chlorine, bromine and iodine. Similarly, haloarenes are represented by ARX, where AR stands for the aryl group or an aromatic group, and X is the halogen atom in this case too. Here X can be fluorine, chlorine, bromine and iodine, just like in the previous case. Now, when we look at these molecules, if we want to simply distinguish between an alkyl halide and an aryl halide by the simplest of possible ways, the best method is to assume that an alkyl halide would have the halogen atom attached to an sp3 hybridized carbon atom. That means the carbon atom would be completely saturated. It will not be part of any double or multiple or triple bonds, but a saturated carbon atom that is sp3 hybridized attached to a halogen atom is often referred to as an alkyl halide or a haloalkane. Then in aryl halides they should be attached to an sp2 hybridized carbon, but most by the term an aryl halide or a haloarene we would mean that they are attached to an aromatic ring or a higher order aromatic compound. So we will look into these classifications and names in the coming slides. Okay. So before I go further, I would also like to say that these kind of molecules are widely used by chemists and also by non-chemists, even without knowing what these compounds are. One of the most common applications of these molecules is that the lower members of this class of compounds are liquids, so they are used as solvents and they can dissolve most of the other organic compounds. So organic compounds, unlike most of the inorganic compounds that we come across, for example sodium chloride, potassium iodide and so on, they are mostly non-polar compounds, they are not ionic. So such compounds needs to be dissolved in suitable solvents, and haloalkanes are normally used as solvents for dissolving these non-polar organic compounds. They also are highly useful as synthetic starting materials. So whenever we would like to prepare organic compounds that contain multiple functional groups, one of the starting points for making these kinds of compounds are organohalogen compounds or haloalkanes or haloarenes. So I would also like to say that normally these organic compounds that contain a halogen atom are called organohalogen compounds or organohalocompounds and so on. So you would find these terms being used interchangeably in between. or just to say that halogen containing organic compounds and so on. So I have a few examples listed here. So you would find that these are also some of the examples that you would find in your book as being mentioned as organic compounds that contain halogen atoms. So first of them here is chloramphenicol. So this is an antibiotic. This particular molecule is an antibiotic. You can see that it has 2 chlorine atoms attached to this. So by antibiotic, it is something that has antibacterial properties. So this can be used against bacterial infections that can cause us various diseases. So this particular compound chloramphenicol is used against typhoid. It is also a good against plague and so on, but it is one that is most commonly used against typhoid. So it has chlorine, it has 2 chlorine atoms, and you would also find that these chlorine atoms are attached to an sp3 hybridized carbon atom. So this is an example of a haloalkane. The second example that I have is thyroxine. So thyroxine is a prohormone, so this is not exactly the hormone that is functional. You would find that it has 4 iodine atoms, and all 4 iodine atoms are attached to aromatic rings. Now in the active form, one of the iodine atom is lost from it, and it would be a triiodo compound, that is the active enzyme, and this particular enzyme is formed in our body, and if you have a deficiency of this, this is taken as a medicine, this is taken orally. So this is just an example to show that this polyhalogen compound, the compound that contains as many as 4 iodine atoms attached to an aromatic ring, is a biologically active compound and something that we produce in our body. The third example is chloroquine. This is used as a medication against malaria. It is also used, it is taken in advance to prevent from getting affected by malaria, or it can also be used as a drug. So this has a chlorine atom that is attached to an aromatic ring. So although this, as you see, is a compound that has 2 rings attached, but the chlorine is attached to one of the aromatic rings, so it is an example of a haloarene. So the first 3 compounds that I showed you are having rather complex structures which are difficult to comprehend. But you have a look at the 4th structure that I have here. This just has 2 carbon atoms, and the first carbon is attached to 3 fluorine atoms, whereas the second one is attached to a chlorine and a bromine. This is called halothane, and this is a general anesthetic. So these are given to patients before they are subjected to a surgery. So this compound would be able to make you not feel the pain or the medical process that a person is supposed to undergo. So this class of compounds simply gives you an idea that the structural diversity of these compounds are quite high, and their applications are also quite a lot. However, while we are trying to use organohalogen compounds, we should be aware of one particular fact, that halogenated organic compounds degrade extremely slowly under natural conditions. That means if it happens to go into soil, if it happens to go into the environment, they generally take quite a lot of time to get disintegrated or decomposed. As a result, they continue to stay in the environment, and sometimes they continue to stay in living organisms, and most of them can cause problems. So therefore, although initially when halogen compounds started to be introduced for industrial applications, they were widely accepted. Nowadays, we would like to limit their usage because they could cause problems to the environment. One of the reasons why they get degraded slowly is because the bacteria that are present in soil are generally not able to decompose them by their normal methods of decomposing organic compounds. So this retains these molecules in soil for longer time. Okay. So now the next thing that we can do is to have a look at very simple examples of this class of compounds, and then try to see how we can classify them, so that whenever we come across one of these compounds, we are able to identify them and put them into a particular class, and then able to understand them better from our perspective. Okay. So the most simple classification that we can have is on the basis of number of halogen atoms. So if you take, first of all, when you see an organic compound that contains a halogen atom, we can have a look at them and see how many halogen atoms are present. So I have ethane molecule that is substituted with a halogen atom here. So this is a monohaloalkane by X, as I have mentioned. I mean either fluorine, chlorine, bromine or iodine. So this is a monohaloalkane, 1 halogen atom is attached to it, and the second one is a dihaloalkane. I have put 1 halogen atom each on the 2 carbon atoms of ethane. So this is a dihaloalkane. So they are normally called as di plus the name of the halogen atom and then the alkane that it corresponds to. And the third one is trihaloalkane, where I have 3 halogen atoms attached to 3 different carbon atoms of a propane based molecule. The Classification continues to be the same even in the case of aromatic compounds. So, monohaloarene, a compound that has only one halogen atom, it can be dihaloarene when there are two halogen atoms present, trihaloarene and so on. It has to be noted that these halogen atoms need not be the same. So, whenever I write an X, one of them can be a fluorine, the other can be a chlorine, the third one can be an iodine and so on, and all those compounds can be made, and most of those compounds are known. Next, we could go ahead and we can say that we should then, once we have identified the number of halogen atoms present in a molecule, the next thing to do is to look at the molecule and see where exactly is this halogen atom attached to the molecule. So, based on that, we could classify them as compounds that contain sp3 hybridized carbon atom, those are saturated carbon atoms attached to a halogen bond. So, this normally all the simple alkyl halides or haloalkanes that we started discussing with. So, most of these compounds fall into this category, and they, as I have already mentioned, are shown as Rx. And a general representation for this class of compounds, provided that there are no unsaturated bond within the molecule, would be CnH2n plus 1x. So, this is derived from the general representation for a saturated hydrocarbon, which would be CnH2n plus 2. So, we have removed one of the hydrogen atoms and put a halogen atom. The simplest example is a methyl halide or a halomethane. So, I have methyl group here attached to an X. Now, I have shown the carbon atom in blue color. This is just because I would like you to concentrate on those particular atom that is attached to the halogen here. And you can see that this C atom is attached to 3 hydrogen atoms, that is when we call it as a methyl group. So, it is a halomethane. And the next example, I have almost the same structure except that one of the hydrogen atom is replaced with an alkyl group. Then in the third structure, I have replaced 2 of the hydrogen atoms with 2 alkyl groups, and I have replaced all the hydrogen atoms with alkyl groups. So, based on the number of alkyl groups that are attached to the carbon to which the halogen atom is attached, these molecules can now be called as primary, secondary or tertiary alkyl halides or haloalkanes. So, once again, these classifications are based on the number of substitutions that are available on the carbon atom to which the halogen is attached. So, a primary haloalkane is one in which the carbon attached to halogen is bonded only to one alkyl groups, and when there are 2 hydrogen atoms present. We call them as secondary when 2 alkyl groups are present, and tertiary when 3 alkyl groups are present. The normal notation, a simple notation, if you do not like to write primary, secondary and tertiary in all cases, would be to use 1 with a degree sign on top, but this should not be read as 1 degree, and this should not be read as 2 degree, 3 degree and so on. Instead, although you write them as 1 with a degree on top, they have to be read as primary, secondary and tertiary. I quite often come across people who mention to this compound as a 1 degree alkyl chloride, 2 degree alkyl chloride and so on, which is not the correct way of calling them. Now, even while I have said that these are compounds that do not have unsaturated carbon atoms attached to halogens, we could also have these class of compounds which are called allelic halides, where the halogen atom, as you can see, is attached to a CH2. So, I would show you this particular carbon here, which I have highlighted. So, this is a CH2 group, it is attached to a double bond and an X. So, this comes under the haloalkane class. So, this is an alkyl halide, and here again the halogen atom is attached to a carbon that is sp3 hybridized. However, the same carbon is also attached to a double bond. So, these kind of compounds where the carbon atom attached to the halogen atom is adjacent to a double bond are called allelic halides or allele halides in general. So, I have 3 such examples. So, here you can see this is an open chain compound, a linear compound where I have a double bond CH2 and X, and the second example is where I have a double bond and on the, so it is a 6-membered carbon ring. So, it is a cyclohexane ring. So, in this cyclohexane I have a double bond, so it is a cyclohexene, and on the carbon that is immediately after the double bond has a halogen atom. So, this again is an allelic halide. And in the third example I have a cyclopentene ring, but now the CH2 that is attached to the double bond is going out of the ring, but it is attached to a halogen atom. So, this again is an allelic halide. So, allelic halides are those class of compounds where you have a double bond that is attached to another CH2 followed by an X. So, out of these three structures, you can see that this carbon is attached to one alkyl groups and two hydrogens. So, this is a primary allele halide, whereas this carbon is attached to two different groups, one double bond and this, and there is only one hydrogen present in this. So, this is a secondary allele halide, whereas this again is a primary allele halide. So, these are the classifications for allele halides. They are all haloalkanes because the halogen is not attached to a double bond, instead it is attached to a saturated carbon atom. Now, the other class is benzylic halide. So, these are compounds where the carbon attached to halogen is attached to an aromatic ring, to be precise to a phenyl ring. So, this is a primary benzylic halide or a benzyl halide where the aromatic ring is attached to a CH2 and an X, and in the second example this carbon is also attached to another R group. That R group can also be an aromatic ring, it can be an alkyl ring too. So, then we call it as a secondary benzyl halide, and if there are two R groups and a phenyl ring, we call it as a tertiary benzyl halide. Now, again out of these two R groups, either one or both of them can also be aromatic rings. So, that does not matter, we still call them as benzyl halide and they would be tertiary because there are no hydrogens attached to the carbon to which halogen is attached. Now, we would go ahead and then talk about compounds containing sp2-CX bonds. So, these are compounds where the carbon that is attached to the halogen is sp2 hybridized. We started off our discussion by saying that aromatic halogen compounds or haloarenes or aryl halides are those compounds where the halogen atom is attached to an sp2 hybridized carbon atom. But you already know that not all sp2 carbon atoms needs to be in an aromatic ring. For example, these two compounds here, the vinyl halides. So, this simply means that I have a double bond and the carbon that is attached to the double bond involved in the double bond is attached to a halogen atom. So, these are examples of vinyl halides. They can be open chain compounds or they can be cyclic compounds. Now, we call only those compounds as aryl halides where the halogen is attached to an sp2 carbon, of course, but to an aromatic ring. The aromatic ring need not be benzene in all cases, it can be naphthalene, it can be any other higher order aromatic rings. But as long as they are attached to the halogen atom is attached to an aromatic ring, they are called aryl halides. So, this is a very simple way of classifying these compounds. Okay. So, now that we have talked about how these molecules can be classified, we will look at their nomenclature. See, you already know that once we know about a particular class of compounds, we would like to give them names, so that whenever we would like to call out a name, immediately a structure associated with the name comes to your mind. So, this is the whole function of nomenclature. So, the term nomenclature is given by IUPAC, which you know is the International Union for Pure and Applied Chemistry. So, now what IUPAC does, what the union does is it sets out a set of rules based on which how chemistry should be seen and discussed by the class of people who follow chemistry. So, one of their main criteria is to set out rules by which compounds can be named in a very systematic manner, so that the name that I am suggesting or I am telling is something that immediately the person who listens to the name is able to associate with a particular chemical structure. So, all of the compounds that we see today can have an IUPAC name. However, some of the compounds were well established, they were already known even before IUPAC started setting out its rules. So, such compounds are sometimes known more commonly by their common names, because the chemicals are so common that people would immediately identify them with common names that were in use for decades. So, based on this, some of the compounds would have an IUPAC name and along with them they would have a common name. Now, if you do not know the common name, that is all right, but you should always be able to write an IUPAC name for a compound. But we would discuss the common names for the most common compounds and then discuss IUPAC name for most of the compounds that we would see here. So, I have examples here to discuss the points with you. So, the first compound I have is a haloalkane that has 3 carbon atoms and it is attached to a bromine atom by one of the sides. So, just like the nomenclature that you studied in IUPAC, whenever we see a compound, what do we do first is we identify the carbon atom that has this particular substitution, then we look at the compound and identify the longest carbon chain. So, in this case it is a straight chain, we do not have any issues with that. So, there are 3 carbon atoms in this chain and it is attached to a bromine atom at one end. So the carbon that is attached to bromine atom is the one we would call as carbon number 1. So this compound has 3 carbon atoms, so it is a propane. So we would be able to call this compound as a bromo substituted propane, and the IUPAC name for that compound would be 1-bromopropane, which means that we have a propane where the bromine atom is attached to the first carbon atom, that means at the end of the chain. Now again this compound is propane, so it is called as normal propyl bromide in a common way. So it has a trivial name which corresponds to normal propyl bromide or N-propyl bromide. So you would also find this name being used. So what I have done is the red colors that I have drawn here are all the IUPAC names and the blue names are the common names. So it is always important that you know the IUPAC names and you are able to write the IUPAC names. Common names are not something which any of us can start giving, because those are already established names that were there. So if you do not know them, that simply means that you have not heard about them. But IUPAC names are something that we are able to give to a molecule even if we are seeing a molecule for the first time. So those are the names that one should practice and be able to give it to a molecule. So the second compound here, so this again is a propane, but this time instead of bromine I have a chlorine, and the chlorine is attached to the second carbon atom. So it is not at the end of the chain, it is in the middle. So then what we do is we start numbering the carbon atoms from one of the sides. So we have 1, 2 and 3, and the chlorine atom is attached to the second carbon atom, so we call it as 2-chloro, and then of course propane, because there are only 3 carbon atoms in the chain. So the IUPAC name for this is 2-chloropropane. The common name is even more interesting. Whenever you have a propane chain, that is 3 carbon chain, and if you put a substitution on the middle carbon, it is normally called as an isopropyl group, or this particular compound is called as isopropyl chloride. So isopropyl is when the substitution is on the middle carbon atom of a propyl group. Now the third example is isobutyl iodide. So you would immediately see that this has some similarities with the isopropyl group, because I would show you 3 carbon atoms that actually looks like a propyl, and the substitution of a CH2I goes from the middle carbon. So that is why in common name it is called as an isobutyl group, and it is an iodide, so we call it as isobutyl iodide. Then again you see it is very difficult to give this common name by yourself, because there are no rules followed in here, but whereas the IUPAC name is something that we can always give to the molecule. So now let us look at the molecule once again. So this is a molecule that has 4 carbon atoms and an iodide, but what we need to do is we need to identify the carbon that is attached to I and then make the longest carbon chain. So no matter which way you go, you would see that you can only make a 3 carbon chain in this. So one of the methyl groups, either this or this, has to be seen as a substitution. So therefore the name of this compound would be 1-iodo-2-methyl propane. This is because between the methyl group substitution, so if I am assuming that this is the chain that I would like to go with, so you see that I start with I, CH2, CH, CH3, and the second carbon atom has a CH3 group. And how do I name it is I give the name in such a way that the name that has the first alphabet in the alphabetical order, that substituent has to be named first. So it has an iodine in carbon number 1, so it is 1-iodo-2-methyl propane. Propane because there are only 3 chains. So it is a very simple rule, but once we start using it, we would be able to name it better. Now I have another example here. This should be rather straightforward. So this is a 4 carbon chain with a chlorine at the end. It is called 1-chlorobutane. It does not matter which side you write chlorine. Chlorine can be written on this side or this side, but as soon as you see a chlorine atom attached to an alkyl chain, you number the carbon that has chlorine atom as the first one. If chlorine is in the middle, then that particular carbon should get the lowest possible number as much as possible. So we will see that example. So this compound here is 1-chlorobutane, and or its trivial name is N-butyl chloride or normal butyl chloride. A careful look at these names would suggest that while all the IUPAC names look like haloalkanes, the trivial names or the common names are corresponding to alkyl halides. So they name the alkyl group first, followed by the halogen that is associated with as a halide. So these names also have more similarity with the inorganic compounds that we call sodium chloride, for example, where sodium is replaced with an N-butyl group. So this has a lineage from all the other chlorides that you would find in nature and different kinds of chemists used to use, but whereas organic chemists would like to call them as 1-chlorobutane, so that their names are pretty clear to everyone who hears them. Okay, so this is one chlorobutane. So the second example here is more interesting, because here I have 4 carbon atom, but the chlorine is not attached to the first one. So now I can start naming this from this end or this end. So if I start naming it from the left hand side, I would see that the chlorine atom is attached to the second carbon atom here, but if I start numbering it from the right hand side, I would find that chlorine is attached to the third carbon. So you should always start numbering from the side in such a way that the carbon attached to chlorine gets the lowest number. So this is 2 chlorobutane and not 3 chlorobutane. So we would always start naming from here. Butane because there are 4 chains, 2 because there is the chlorine is attached to the second carbon, chloro because it is a chloro. So if I replace chloro, it would be with bromine, it would be 2 bromobutane and so on. And this compound is its common name is secondary butyl chloride and sometimes written as S-butyl chloride, because here in butane the chlorine is attached to a secondary carbon atom, a carbon atom that is attached to 2 alkyl groups. So it is called a secondary butyl chloride in its common name. Now the third one here is something that we have already seen. It is similar to this compound here that I have the isobutyl iodide that we have already seen. So this is isobutyl chloride. It has to be named as 1-chloro-2-methyl propane. So that is the IUPAC name. So I assume that you do not have any issues with this. Now have a look at the last compound I have on this slide. So this particular compound has a rather interesting structure. It is a carbon atom that is attached to 3 CH3s and a chlorine atom. So definitely this is a tertiary haloalkane, because the carbon here which is attached to chlorine atom is already attached to 3 alkyl groups. But to name this compound properly in following the IUPAC rules, what we need to do is we look at the longest alkyl chain that has chlorine atom on it. So you can see that there is a CH3, a C attached to Cl and a CH3. So once you consider this particular alkyl chain, you would find that it has a CH3 attached to the carbon that is attached to chlorine. So because the longest chain has only 3 carbon atoms, it is a propane, and the chlorine atom is attached to the middle carbon, so it is 2-chloro, and the same carbon is also attached to a methyl group, so it is 2-chloro-2-methyl propane. So this is the way we would name it. So we would name this compound with the longest chain being propane, we will call it as a propane with a chloro and a methyl substituent. Now which one to name first? We would always name chloro before methyl, because chloro starts with a C which comes first in the alphabetical sequence, and methyl comes second because it has an M. And the names, the numbers have to be such that these substituents have the lowest possible numbers. Now I have other class of compounds. So we have left the simple haloalkanes there, and we are going further and looking at these compounds that have double bonds. So see, what you see here is an ethene molecule. So you know, all of you know ethene. Ethene is CH2 double bond CH2. Now one of the hydrogens is replaced with a chlorine atom, so it is called chloroethene, and its common name is vinyl chloride. So there is no particular reason why it is called vinyl chloride. The compounds that are attached to a double bond, a simple double bond, are called vinyl compounds. So if it is a chloride, we call it as a vinyl chloride. So this is a common name. All of you might have heard PVC, polyvinyl chloride, which is a polymer that is actually obtained by polymerizing this particular compound, but that is a common name for the compound. The IUPAC name is chloroethene. So it is ethene attached to a chlorine atom. Now I have a second example. This is something we have seen. This is an allelic compound. It is an allyl bromide, but the IUPAC name does not allow you to call it as an allyl bromide. Instead, what we would call it as is a propene derivative, because there are 3 carbon atoms and a double bond, and you would know that propene is the parent hydrocarbon here. It is no more propane because there is a double bond. So propene is the parent hydrocarbon, and the bromine atom is attached not on the double bond but on the carbon that comes after the double bond. So we would start numbering this molecule in such a way that the double bond gets the lowest possible number. So the double bond starts from carbon number 1, it goes to carbon number 2, and in the third carbon we have the bromine atom attached, so it is called 3-bromopropene, and we put a 1 in the middle just to tell you that the double bond is actually on not on the carbon that has bromine. But once you mention 3-bromopropene, it is pretty evident that the double bond is not exactly on the carbon that has bromine atom. However, a more appropriate way of numbering this would be 3-bromoprop-1-ene. 3-bromopropene is also fine. Now this compound, this is something again something we have seen. This is a benzyl compound. This is benzyl fluoride because benzyl group is attached to fluorine, but the IUPAC name is quite interesting here because this has to be seen as a methyl group that is attached to a phenyl and a fluorine. So we call this as fluorophenylmethane. It is not phenylfluoromethane. This can also be given a different name. It can also be called as a methyl fluoride attached to a benzene. So, it is fluoromethane benzene is methyl benzene is another name for this, but you can always see it as a methyl group attached to fluorine and a phenyl ring. So, it is called fluorophenylmethane in IUPAC. Okay. So, now we will go ahead and we will look at polyhalogenated or dihalogenated compounds. So, here I have ethane molecule that is attached to 2 chlorine atoms. So, I am talking about the example here in the middle sequence, the first one. So, it is an ethane molecule that is attached to 2 chlorine atoms. We call it as 1,1-dichloroethane. This is just because the chlorine atoms are on the same carbon atom. So, we give and when 2 substituents are attached to the same carbon atom, we number it, we give the number twice. So, we say 1, 1. So, it is 1,1-dichloroethane and its trivial name is ethylidene chloride. So, it is ethylidene actually comes from a concept that it is something that is similar to having a double bond, because here we have replaced 2 hydrogen atoms. So, these compounds are called as ethylidene chloride in the common name. So, something you would know only if you know the names by heart, but whereas the IUPAC names are always something that we can give. So, the second compound here is 1,2-dichloroethane. So, this is an isomer of this. The second compound is an isomer of the first one, except that the chlorine has moved to the second one. So, we say that it has 2 substituents on 1, 2 carbon atom, and then it is an ethane, 1,2-dichloroethane, and it is normally called as ethylene dichloride. You know what ethylene is? Ethylene is ethane. So, it is as if chlorine has added on to an ethene or an ethylene, and 2 chlorine atoms are present on each of the carbon atoms of an ethylene to start with. So, therefore, we call them as ethylene dichloride in the common name. These 2 compounds also have a very interesting name. Sometimes people refer to them as this one as a geminal dihalide. So, by the term geminal, what we really mean is that both the halogen atoms are attached to the same carbon atom. So, then we call it as geminal dihalide. If the halogen atoms are attached to adjacent carbon atoms close to each other, then we say both these halogen atoms are in the vicinity of each other, then they can be called as vicinal dihalides. So, these are 2 names. So, this is a geminal dihalide, this is a vicinal dihalide. So, you might come across these names being used in organic chemistry. That only means that whenever you hear the term geminal, which is the short form is GEM, G-E-M. So, that means that both the halogen atoms are on the same carbon atom, and vicinal means they are on adjacent carbon atoms, not too far away from each other, but on adjacent carbon atoms. The third example is a methane derivative. 2 halogens are attached to methane. It is called dichloromethane. So, the IUPAC name is very simple. We say chloromethane, and if there are more than 1 chlorine, then we add a prefix to that. So, in this case di, because there are 2 chlorine atoms. So, it is dichloromethane. And the last one is tribromomethane, because there are 3 bromine. The trivial names for these 2 compounds, dichloromethane is methylene chloride. So, it is similar to ethylene, because 2 hydrogen atoms are replaced with chlorine, and the last one has a more interesting name, bromoform, and the corresponding chlorine analog is chloroform, which you already know. Bromoform and chloroform are also accepted by IUPAC, although they are not according to the strict rules of IUPAC naming. They are terms similar to benzene, toluene and so on, which can be accepted. Okay. Now, I have put the final example here so that we can summarize all the points that we were discussing. So, the compounds that I have, each of these compounds are pentene. So, they all have 5 carbon atoms present in them, but their IUPAC names vary. If you follow the rules properly, we will be able to name them, and they do not necessarily have common names. So, these compounds are complex enough that they are not commonly named. So, a person who wants to talk about this compound will not have a name that he can immediately remember and say. So, they only have IUPAC names that we use, but IUPAC names, even if you do not know, is something that you can give. So, that is the advantage. So, let us look at this molecule. So, this molecule has a double bond and it has a bromine atom. We said because the double bond changes the name of the compound, the parent hydrocarbon is now known as a pentene. It ends with an ENE, not an ANE, which corresponds to alkanes. So, it is an alkene. So, the double bond should get the smallest number, the lowest number possible. So, we start naming from this end, from the CH3, so that this particular compound gets the number 2. Then the double bond continues to the number 3, and finally the bromine is attached to the 4th carbon followed by CH3. So, you can see that there is a longest aliphatic chain, and that chain has a double bond between carbon number 2 and 3, and bromine is attached to the 4th carbon. So, we call this compound as 4-bromo pentene because it has 5 carbon atoms, pent 2-ene because the double bond is on the second carbon. So, this is called 4-bromopentene. Now, let us look at the second compound. Here again there are 5 carbon atoms, but if you look at this, we would only be able to draw 4 carbon chains, and this CH3 here has to be always seen as a substituent, and we would name it in such a way that the double bond, as I mentioned before, gets the lowest number. So, the double bond starts from 1 of the n, so we would start numbering 1 on the CH2 that has the double bond, CH2 double bond, and the bromine is on the third carbon, and there is a CH3. So, the CH3 which is here, this has to be seen as a substituent. So, this CH3 is a substituent here. So, therefore, when we try to name it, we say that bromine is on the third carbon atom, 1, 2, 3, third carbon atom. Then the methyl group is on the second one. So, it is 3-bromo, 2-methyl, and it is a butene because there are only 4 carbons in the longest chain. So, 3-bromo, 2-methyl, but 1-ene. So, this 1-ene would immediately tell you that the double bond is on the first carbon. So, what is good thing with these IUPAC names is if this compound is given to anybody, and if anybody follows the IUPAC rules strictly, they will all come up with the same name. There is no, even if the compounds are being seen for the first time, they would be able to write a unique name following these rules. Similarly, if this name is given to you and if you are asked to write a structure, if you know IUPAC rules, you will only draw one structure that corresponds to this molecule. So, that is the interesting fact about this. That is, this is the exact reason why the International Union for Pure and Applied Chemistry that comes up with this set of rules, so that every compound, every organic compound that we come across can be named uniquely and can be distinguished based on the name. So, let us look at the last compound to complete this. So, this again has a methyl group as a substituent in a 4 carbon chain. The bromine is attached to the last one, but we would always have to name this compound in such a way that the double bond gets the smallest possible number. So, it does not matter if a number from here or from here, the double bond is always starting from the second carbon. Then we would start naming it from the carbon that is attached to bromine, because then the bromine substitution also gets a lower number. So, this compound has to be named as 1-bromo and a methyl group on the second carbon, 1-bromo, 2-methyl, but 2-ene. So, this is the important thing. If we start naming from the other end, what we would name this as a 4-bromo, 3-methyl, but 2-ene. So, although the double bond is still on carbon number 2, the substituents methyl and bromine goes on to carbon number 3 and 4. So, we should not allow that to happen. We should always name it in such a way that these two substituents also get the lowest possible numbers as much as possible. So, this has to be named as 1-bromo, 2-methyl, butene. So, with this I will stop naming the aliphatic compounds, the haloalkanes, and I would go forward and start talking about haloarenes. So, all haloarenes normally do have the same common name and IUPAC name. So, for some reason they from even before the IUPAC had set out the rules, they always were being called as haloarenes. So, the simplest one here, I have a bromobenzene here. So, it is called bromobenzene in IUPAC as well as in common men. So, it is never called as benzyl bromide, because you know benzyl bromide is something else. It is not even called as phenyl bromide or anything. It is normally called as bromobenzene in the IUPAC nomenclature as well as in the common way of calling these molecules. Now, if I have 2 bromine atoms, again it is very simple in IUPAC, you just number it in such a way that these 2 bromine atoms get the lowest possible number. So, it is 1,2 dibromobenzene. So, the only difference in common naming is, so you have learned these terms ortho, meta and para. So, if the substituent is on an adjacent carbon atom, you call it as ortho dibromobenzene. If it is 1 carbon away from each other, then we call it as metadibromobenzene, and if they are on a 1,4 position, then we call it as paradibromobenzene. So, ortho, meta and para are associated with the common naming pattern, whereas 1, 2, 1, 3 and 1, 4 are the ways of naming these compounds in IUPAC. Now, here I have put an example quite intentionally here. So, here you can see that there is a bromine atom and there are 2 chlorine atoms. So, now how do we name them? Where do we start to name them? So, if I call the carbon that has this chlorine as 1, then I have the second chlorine atom on 2 and the bromine atom on carbon number 4. But whereas if I start numbering from bromine, then I would see that the carbon number 1 gets bromine, then 3 and 4 gets chlorine. So, although the first carbon in both cases are substituted, the second substituent here, so I would try to write these numbers here. So, I hope you would be able to see them better when I do that. So, what I would number is, I will call this as 1, 2, 3 and 4. So when I do that, you are able to see that the substituents are on 1, 2 and 4th carbon atoms. Now on the other hand, if I go ahead and start numbering bromine as 1, so I can also give this number here. If I call this as 1, this as 2, this as 3 and this as 4. So this is another way of naming it. So then bromine atom is on the first carbon, then my second two substituents are on third and fourth carbon. So this is something that I don't want, because then my numbers are going higher. So you should always name it in such a way that when you look at the number as a whole, when you sum up these numbers, you get the lowest possible number. So therefore we would name it as 1, 2 and 4 substituted compound. But now what do we write first? Do we write chloro first or a bromo first? Of course we write bromo first. Even if the bromine is a substitution on carbon number 4, we do number that first. We do not associate the number associated with that particular substituent. We only look for the alphabet. So in this case, although bromo is on the 4th carbon atom, it is B comes first in the alphabetical order. So therefore we call it as 4-bromo 1,2-dichlorobenzene. So this has to be the name. Any other name that you give to this compound according to the IUPAC rules will be wrong. Okay. So now look at the last compound that I have. So this is a compound that has a chlorine atom and a CH3. So we know a benzene ring attached to a CH3 group, attached to a methyl group, is toluene. So toluene is also an accepted IUPAC name. So benzene, toluene, both these are accepted. Otherwise you can also call it as methyl benzene, because IUPAC also accepts this name. So in this compound you see that you have a 1-chloro-2-methyl benzene. So you would name chlorine as 1 because chlorine in this case is the first alphabet that comes. C always precedes them. So that is why we call it as 1-chloro-2-methyl benzene, or it can also be called as 2-chloro-toluene. So it is toluene with a substituent on carbon number 2. However, in the common system, this molecule is a toluene molecule with a chlorine atom on ortho position. So it has to be called as orthochlorotoluene. So this is generally about the IUPAC names and common names. Try to remember all the common names that you can, means as much as possible. If something that you see very often and if people refer to them by common names, whenever you come across them, it is okay to know them, it is okay to remember some of those. But even if you cannot, it is not a big mistake, because you are not supposed to remember all the names that you see. You may have to remember a few of them, like secondary butyl, isopropyl, isobutyl and so on. But other than that, all the other common names are something that you may even skip. But make sure that you are able to give a number, proper IUPAC number, to any molecule that comes your way. So you should be able to follow these rules and name them correctly. Your textbook has a lot of examples. Your textbook has even some problems that are associated with this nomenclature of this compound. So I would suggest that you write them down and make sure that you are able to write all the IUPAC names possible. Okay. So now we have already discussed about how we can name these compounds. So now you are able to give names to these compounds. So once we are able to do that, the next thing is now we start really looking at the chemistry of this compound. So you see a organohalogen compound, you are now able to identify this. Even if you are not able to identify, you are now able to give a proper name to it so that another person can listen from you about the compound that you are talking about. But the next important thing is now we start talking about reactions of these compounds and also about how these compounds can be prepared. So once you do not have a haloalkane, you want to make them, how do we make them? So to know that, it is always important that we know what exactly a halogen atom does to a carbon atom when it is linked. So of course you would have guessed that haloalkanes have different properties in comparison with simple hydrocarbons. Why are they different? So simply speaking, a halogen atom is more electronegative than a carbon atom. So whenever you have a carbon atom attached to a halogen atom, it is no more like two carbon atoms attached to each other. Now we have a carbon that is attached to a more electronegative atom. All the halogens, group 17 elements, are more electronegative than carbon. So what do is they try to pull electrons more towards them. So when a carbon and halogen atom are involved in bonding, the electrons that form the bond are pulled more towards the halogen and away from carbon atom. As a result, as I have shown in this slide, you will see that the carbon always feels slight positive charge because it has already contributed an electron for the bond, but that electron is now has moved a little more towards halogen than carbon would have liked. So therefore now carbon has a slight positive charge and the halogen is happy to retain a negative charge. So if we want to draw this bond, it may be even ideal to draw a slight positive charge which is normally represented by a small delta sign, delta positive and a delta negative. So the delta positive resides with carbon atom and delta negative resides with halogen atom. So this is to say that this particular compound now is polarized, this particular bond now is polarized. So all organohalogen compounds are generally polarized. So these bonds are polarized, so these molecules have a dipole moment, and the dipole moment, as you know, is normally measured in dBs, in the unit dB. Okay. Now I have listed the methyl halides here, so the halomethane molecules. So starting with fluorine, chlorine, bromine and iodine. So I have fluoromethane, chloromethane, bromomethane and iodomethane on my table here, and the left hand side column. So in this column you would find them, and what I have in the immediately following column is the bond lengths. So you can see when carbon and fluorine are attached, the carbon fluorine bond length, so these are given in picometers. So the carbon fluorine bond length is 139 picometers. So or 1.39 angstrom. So you would find these bond lengths are increasing as you go down. So when you go from fluorine to iodine, there is a large difference in the bond length. This is expected, right, because bond length is exactly the distance between the center of the atoms that actually form the bond. So when you have a larger atom like iodine, so because iodine is very much lower down the group, so you would find that iodine is very big in comparison with fluorine. So therefore when an iodine and carbon bonds together, the bond is longer, and it goes sequentially. So the carbon chlorine bond is longer than the carbon fluorine bond, carbon bromine bond is longer than the carbon chlorine bond, and carbon iodine bond is longer than carbon bromine bond. So that is expected. So this is the trend you would find. Now what about the bond strengths? Which bonds are more stable? So you can also see that the methyl group, when it is attached to fluorine, the carbon has a 2 sp3 hybridized orbital, right? Carbon falls in the second period, so it has its valence electrons in the second orbital. So you would find that it has a 2 sp3 orbital that forms the bond, and so is fluorine. So therefore these two are of similar size, their orbitals are of similar size. So therefore according to the very classical concepts of bond being formed by overlap of orbitals, you would find that we actually have two orbitals that are almost the same size. So therefore their overlap would satisfy both the atoms that are involved. So you get a bond that is pretty strong, and the orbital overlaps are rather complete. So this results in an extremely strong bond, and that is reflected in the enthalpy of formation of this bond. So you would find that 452 kilojoules per mole for a carbon fluorine bond, whereas it comes down to 234 for a carbon iodine bond. So imagine iodine coming with its big orbitals, and whereas the carbon now only has a smaller orbital to offer. So whenever they overlap, the overlap is not completely satisfactory. So you would find that the bonding itself is slightly weakened, and as a result you would always find that the bond energy of a carbon iodine bond is weaker than a carbon bromine bond, which is weaker than carbon chlorine bond, and the carbon fluorine bond being the strongest. Now what about the dipole moment? There isn't much difference. So you would see that all the halogen atoms, as I have mentioned, are more electronegative, and then there is this difference in patterns of bonding, difference in patterns of bond energies and so on. So ultimately the dipole moment is not much different. They all fall in 1.8 near about, except for carbon iodine bond, because that is the weakest of all. So in this particular case, so iodine starts to get less and less electronegative. So only in this case it is slightly lower. Then again it is not too lower, it is 1.64. So all these carbon halogen bonds are polarized. They all have dipole moment and comparable dipole moments, except for carbon iodine bond, which is reasonably lower than the others. So this gives you a fairly good idea about how a CX bond is. So whenever you see that there is a halogen attached to a carbon, immediately remember that the carbon is positively charged, or in other words the carbon now is looking for electrons, whereas the halogen is ready to leave with a negative charge. It has already pulled the electrons from carbon towards itself a little bit. Now it is ready to leave carbon and leave carbon with a positive charge. So once carbon gets electrons from somewhere, it would allow the halogen to leave. So this has a lot to do with the way organohalogen compounds or haloalkanes react. So we would come to their reactions later. So this is something that is worth remembering as we go along. Okay. Now, since we have talked about all these things, the next thing that I would discuss is about the preparation of haloalkanes. So how can haloalkanes be prepared? So the most simple preparation of haloalkanes should of course be from the most available set of molecules. So the most easily available molecules are hydrocarbons, right, because they come from petrochemicals. After that, those are alcohols. Now alcohols are a good starting point for the synthesis of many organic molecules, just because the hydrocarbons are now already functionalized, there is already a carbon oxygen bond. So if we want to functionalize an alcohol, all we need to do is break the carbon oxygen bond and put the new bond there. So therefore the preparation of haloalkanes also do start from alcohols, the simplest of them, I mean. So now I have a very simple reaction written here. The first one, if you see, I have an alcohol which is represented as an ROH, where R stands for the alkyl group, OH for the hydroxyl group that results in the alcohol structure. So when an alcohol is treated with a hydrohalic acid, hydrochloric, hydrofluoric, hydrobromic, hydroiodic and so on. So when it is treated with a hydrohalic acid, what do we get is a haloalkane plus a water molecule. So now if you would like to know how this may be happening, why did this break, what exactly happens is the hydrohalic acid dissociates, right, it dissociates in solution to H plus and X minus. Now this H plus that is present in any acid, for example, would like to interact with the oxygen atom of the alcohol, and it would protonate the oxygen atom of the alcohol. So if you look at the alcohol here, the O is already bonded to an R group and a hydrogen. Now if another H plus comes and binds to oxygen, so it is an H plus, it does not have an electron, it comes and binds with oxygen, so the oxygen is protonated and oxygen gets a positive charge. And because of the positive charge now, this OH2 group is actually like a water molecule. So what I mean to say here is that now your ROH, when you treat it with an H plus, becomes ROH2 positive. So this particular group has retained a positive charge. So now this is something that would like to go out as water. So that leaves your alkyl group wanting a new group. So we already mentioned that hydrohalic acids are polarized. So I have H plus and X minus. Now when water leaves, what does this R needs is something with a negative charge. So this would then react with the X minus that is present there and would give you Rx. So this is how alkyl halides are made from alcohols. So if you take an alcohol and put it with an HX, hydrohalic acid, we would get the haloalkane, which I have shown here, along with a molecule of water. So you would see that water comes out. So that is the simplest way of representing this reaction. Now, but not all alcohols give you the reaction with the same ease. The general order of reactivity is tertiary reacting faster than secondary, reacting faster than primary, and methyl reacting the slowest. Now primary and secondary alcohols react with HX, that is hydrohalic acids, effectively only in the presence of zinc chloride as a catalyst. So otherwise the reactions do happen, but they are extremely slow. You may have to heat it, you may have to leave the reaction for a longer time, whereas tertiary alcohols would react immediately with HX. So why is this different? So it has some relation with the equation that I have written here. I have shown that the OH gets protonated and this R starts to feel the positive charge too. So generally the one that can hold this positive charge better, so the alkyl group that can hold a positive charge better would be the one that reacts better. And you would later also see that tertiary alkyl groups are better in handling a positive charge, better in handling an OH2 group, leaving away from it. So that is the reason why it reacts faster. But once you go into secondary and primary, the reactivity therefore reduces. Now what exactly does zinc chloride does is zinc also has an affinity for oxygen. So therefore when you take zinc chloride, which is a Lewis acid, it binds to O even before hydrogen binds to it. So therefore it allows the breaking of the carbon oxygen bond and removal of the hydroxy groups faster. So that is why we use a catalyst in this reaction. So zinc chloride can help if the reaction is slow. Okay. Now sometimes you would have heard about hydrochloric acid, you would have gone to your labs and then seen that there are hydrochloric acids present in your lab, in most of the labs in your schools. But now some of the other hydrohalic acids are not commonly available. We may have to make them in the reaction mixture. So one simple way of doing it is to take an alcohol like before and treat it with sodium iodide or potassium iodide, sodium bromide or potassium bromide and so on, along with an acid. So if you are using sodium iodide to make an alkyl iodide, all you need to do is you do not have to use hydroiodic acid. You may be able to use a sodium salt of iodine and then put an acid along with this. So in this case you can use phosphoric acid. So what it would give is the alkyl iodide along with the sodium or potassium salt of phosphoric acid. So therefore you can also use an acid with a salt that might in situ in the reaction mixture generate the hydrohalic acid that you need. A preparation of alkyl bromides is given here. So you take alcohol, treat it with sodium bromide and H2SO4, then we will get the alkyl bromide and a sodium salt of it plus water. So this is a very simple way of making this molecule. Okay. So continuing with what can be done with alcohols, I will show you another example here. So if you take alcohol and treat it with phosphorus trihalide. Phosphorus has an affinity for oxygen, so it would be able to pull oxygen out of any molecule. So there are 3 halogens, so 3 molecules of alcohol can react with this and then give you a haloalkane along with phosphorus acid H3PO3. So instead of using a hydrohalic acid, you can also use PX3. And sometimes when the X is bromine or iodine, you do not even need the phosphorus trihalide. You can always make it in situ from red phosphorus and the corresponding halogen. So in that case, you can take alcohol, treat it with red phosphorus and the halogen, and you would generate this PX3 species in situ and get this molecule. You can also do the reaction with PCl5 if you want a chloride, then the product that you get is POCl3 as the side product along with HCl and alkyl halide. So here again you can see that phosphorus pulls out this oxygen and HCl goes out, and then one of the chlorine atoms goes and attaches with this. The final reaction is the one with thionyl chloride, and the most interesting because thionyl chloride when it reacts with an alcohol gives you RCl, then sulfur dioxide and HCl. These 2 byproducts that are formed in the reaction are gases. You will always end up getting the alkyl halide that you want, so in this case chloride because you are using thionyl chloride. So along with the alkyl chloride or the chloroalkane, you get sulfur dioxide and HCl. These 2 are gases, so they escape from the reaction mixture and you end up having just the product you want. So to summarize what I wanted to say about the preparation so far, this is the simplest synthesis possible. You make them from alcohols, you can treat them with HX, you can treat them with phosphorus halides, or you can treat them with thionyl chloride. The one using thionyl chloride to make alkyl chlorides is the most easy one to do because the byproducts are gaseous. So I would stop here for this class, and then we will continue to discuss the preparation of haloalkanes in the next class. Thank you.